So when we brought up the concept or the idea of a non-volatile solute, what we talked about is that it lowers the vapor pressure of a solvent so that the solution always has a lower vapor pressure than the pure solvent does. What that looks like on a phase diagram is shown on the right. And here we have the pure solvent. This is a vapor pressure curve. This is a freezing curve, the solid liquid transition, and this is the curve for sublimation. And again, this is the triple point where the three meet. Well, if you lower the vapor pressure of a liquid, so let's say this is its normal boiling point when it's a pure solvent, then when you add a non-volatile solute, we drop the vapor pressure of that substance. And then in order to get it to boil, what we have to do is we have to increase the temperature of the solution again. So you can take a solution actually that's boiling, throw a solid in it that will dissolve. It will stop boiling because now its boiling point is higher than it was before, and then you'll have to increase the temperature to get it to boil again. Now, notice what happens at the other end of the curve. Since you're lowering the vapor pressure at all points on the curve, it intersects the transition between the solid and gas at a lower temperature. This also causes the liquid-solid transition to shift backwards as well. So what we end up getting is a boiling point elevation on one side. That's a TB down here. And a freezing point depression going the other way. Now, of course, this is called an elevation because it's going up, and this is a depression because it's going down. Turns out both of these can be calculated using the same form of an equation. So to calculate the boiling point elevation, the equation is given as TB, or sometimes it's delta TB, okay, is equal to K B times M, where M is the molality of the solute particles. Now, if you're using ionic compounds, right, then each ionic compound will break down and give you more ions. And so we use a slightly different form of the equation. This is known as a Van't-Hoff coefficient, and for sodium chloride that value is very close to 2 because sodium chloride gives us 2 ions for every mole of substance that dissolves. And then for the freezing point depression, TF, that's usually calculated as KF times M, where again M is molality. Now KB and KF are boiling point elevation constants and freezing point depression constants. And this leads us into something called colligative properties. Boiling point elevation and freezing point depression are part of a group of properties known as colligative properties. So colligative properties don't depend on what the particle's identity is. It only depends on the number of particles that are produced. So and another important feature is that the properties are solvent properties. Since the identity of the particle doesn't matter, it turns out the properties that we're looking at are dependent on the solvent. Very much for the same reason when we were looking at Raoult's law for non-volatile solutes, right? It's really the mole fractions of the solvent that matter in the property, and it doesn't really matter what the other substances are in the solution. It just matters what the mole fraction of the solvent is. So colligative properties are very much like those. Now, when we talk about these, strictly speaking, we're talking about non-volatile solutes, but if you have solvents with very low vapor pressure or solutes that have very low vapor pressure, it can behave the same way. Now, if the solid is like sodium chloride, the one thing about ionic compounds that's important to understand is that they tend to produce more particles than there are moles of substance. For example, 1 mole of sodium chloride theoretically can produce 2 particles, and magnesium bromide could theoretically produce 3 particles. As it turns out, this has been tabulated. How much of an effect ionic compounds can have has been tabulated, and they're called Van't-Hoff factors, and they're usually done for relatively dilute solution, and we just assume they apply roughly to the calculations that we're doing. So it says Van't-Hoff factors at 0.05 molal, right, concentrations of aqueous solution. Non-electrolyte, that would be molecular compounds, have I values of 1. So when we're doing the, for example, delta T is equal to I times KB times M, right? If the substance is molecular, we treat I as 1. But for sodium chloride, theoretically it's 2, but because of ion pairing and other factors, it ends up being about 1.9. Magnesium sulfate has larger charge magnitudes, +2 and -2, and that actually has an influence on its Van't-Hoff factor. So instead of being 2 particles being produced, it behaves more like 1.3. So there are deviations dependent on charge. For the most part in this class, unless you're given the Van't-Hoff coefficient, then we're going to assume it is exactly what it says it is for the formula. Now, just a couple other examples. It can deviate quite a bit. Here's 4 particles and you get 3.4, right? 3 particles, 2.6. In general, though, compounds like sodium chloride are very close to what we would expect theoretically. So how would you calculate a boiling point or a freezing point change as a result of having a non-volatile solute? So suppose you had a 0.5 molal solution of, let's say, glucose. So that's C6H12O6. First thing you have to recognize is that this is a molecular compound. Then you would assume that, for example, the delta T, or sorry, the T boiling, let's say the boiling point elevation, would be I, right, which times K B times M. That would be equal to 1. Now, the value for KB, we would look it up for, if it's an aqueous solution, we would look it up for water. So water, KB is here. It's 0.512 degrees Celsius per molality unit. So this is 0.512 degrees Celsius per molality unit, and then we would multiply that by 0.5 M. So that comes out to be 0.256 degrees Celsius. So what's the boiling point of the solution? Well, you assume that it's an elevation because it's a boiling point. And then what you do is you add this value to the boiling point of the pure solvent. So in this case, we would go to water, and here's its pure boiling point, 100 degrees Celsius. And so the T, the boiling point, will be 0.256 degrees Celsius plus 100 degrees Celsius. And that would give me approximately 100.3, rounding to the correct number of sig figs, like that. Here's another example. It says calculate the freezing point of a 1.74 molal solution of naphthalene in carbon tetrachloride. So again, naphthalene is a molecular compound. So we're going to have TF is going to be I, right, times Kf times m. And then for I, if it's molecular, we give it a value of 1. And then Kf, we have to look up the freezing point depression constant for carbon tetrachloride. So this would be carbon, CCl4. And we would look it up on our chart, and it has a freezing point depression constant of 29.9 degrees Celsius. So this becomes, 29.9 degrees Celsius per molality unit. Okay. And our molality is 1.74 molal. So that ends up being 52.0 degrees Celsius, because the molality units will cancel. Now, so what's the freezing point of carbon tetrachloride? To do that, what you have to do is you have to go back and look at the normal freezing point for carbon tetrachloride. So it's minus 63.5 degrees Celsius. So this is a depression, right? So it's 63.5 degrees Celsius minus 52.0 degrees Celsius minus 115.5 degrees Celsius, or negative 115.5 degrees Celsius. So in order to calculate the freezing point, always remember it's a depression. So you take the current freezing point and you're going to subtract that off the freezing point depression off of the actual normal freezing point to get the freezing point, the depressed freezing point. Hopefully I said that right. So this is your new freezing point for that solution. So the last of the colligative properties that we talk about is osmosis and the idea of what's called an osmotic pressure. So osmosis has a kind of a weird definition. It's very context specific, and the idea is this: osmosis is the movement of water, so it particularly has to do with water, through a semi-permeable membrane. So let's look at what normal osmosis does. So this is an illustration from your book, and they have this tube. It's called a U-tube, of all things. And first you think of it as being filled with water, right? And then on this side, we've added solute particles, again, non-volatile solute particles. Right? And what happens when you allow the water to flow? Well, the movement of the water through this membrane, okay, causes water to go from the right-hand side to the left-hand side. Now, the nature of the semi-permeable membrane is that, in principle, it only allows water to pass. That's why they call it semi-permeable. And in essence, what the water is trying to do is to dilute this solution and increase the entropy on this side of the solution. Because if you think about particles in a liquid, right? What that creates is a situation of entropy, and it turns out in nature there's this natural tendency to go to higher entropy. So if you think about it like this, right, then the water wants to move from the side with no solute to the side with solute. It'll actually move it enough that you'll see a difference between the levels of water on one side and the other. The pressure that's represented by this difference in liquid from this side to this side is known as the osmotic pressure, and it has an unusual equation for calculating it. The equation will look maybe familiar, but it has to do with P, right, is equal to N over V times RT. And what is that equation, right? That's the ideal gas law. Most commonly, though, when it's referring to osmotic pressure, what it's given as is pi, this is the osmotic pressure, is equal to big M, that's molarity, because we're talking about a solution, so N over V is the molarity, times RT. Again, if it's molecular in nature, then there's a Van't-Hoff factor that goes in front of here that's 1. But if it's ionic in nature, then there's a Van't-Hoff factor that goes there that's approximately 1.9. So if you can calculate the molarity of the solution, you can calculate the osmotic pressure. That can tell you in the ideal situation how high this side of the liquid will be relative to this side. I have a couple of little videos to illustrate osmotic pressure. Oh, by the way, this R, right, is just the ideal gas constant, 0.08206 liters, moles, atmospheres, Kelvin.
When a solution and a pure solvent are separated by a semi-permeable membrane, solvent can flow in both directions, but the solute cannot. Here, pure water moves into the solution, working to bring both the solution and pure water to the same concentration. This process, osmosis, continues until the flow of water across the membrane is balanced by the pressure exerted by the water column.
There's another short illustration.
A semi-permeable membrane blocks solute molecules, but allows solvent molecules to pass in both directions. The number of solvent molecules moving from the solution side to the pure solvent side is less than the number moving into the solution side, resulting in a net flow into the solution.
So honestly, this is a little bit of a misconception on how osmosis works. They talk about the particles blocking one side or the other. But what is true about it is there's more water molecules flowing from the side of low concentration to the side of high concentration. So with that, I'm going to move into a slightly sort of gray area for chemistry. We're going to talk a little bit about how osmotic pressure can affect red blood cells. So there's a unit called a milliosmol or milliosmolarity, and it's the same as molarity, except that when we're talking osmolarity, we're typically talking about the molarity of solute particles that can affect the osmotic pressure. So a term that goes along with osmolarity and osmotic pressure is the concept of hypertonic, hypotonic, and isotonic. Now you'll often hear isoosmolar, which is oftentimes believed to be the same molarity, but really it means it has the same osmotic pressure. And then that also gets equated with the term isotonic, which means there's no net solution flow. So what I've shown here, I'm going to try to tell you what the difference of these things are, because it's not really clear. So these are examples of red blood cells, and these are normal red blood cells. That means they're in an isotonic solution. So what an isotonic solution is a solution where there is no net fluid flow from outside the cells to the insides of the cells. In other words, there's a rate of liquid going in, water, and a rate of water coming out, and they have the same tonicity then. Now, if we change the outside solution and we make it hypertonic, okay, then what will happen is water flows from the inside of the cell to the side that's hypertonic. This means the cells shrink and they take on this unusual appearance. Now, if you put it in a hypotonic solution, then what it means is there's a net flow of water from the outside of the cell to the inside of the cell. So the water is moving like this. Now, when we say that, then actually hypertonic and hypotonic are two sides of the same coin, because when we say the water moves from inside the cell, oops, all right, we'll try that again. So when we say that water is moving from inside the cell to the outside of the cell, it means that the inside of the cell is hypotonic relative to the outside. And then when we say that it's hypertonic, or when we say it's hypotonic on the outside, really what that means is it's hypertonic on the inside. And this actually doesn't have to do with the concentration of the solute just by itself. For a lot of ionic compounds that can't cross the membrane of the cell, these two terms, this hypertonic and hypotonic and hyperosmotic and hypoosmotic, can be the same. But it turns out there are a lot of organic materials that can cross the cell membrane. So if you have a let's go back here. So this is supposed to be isotonic, right? This is when water flow inside to outside's the same. Now, if you make it isoosmotic, that just means it has the same osmotic pressure. But if you take a solution of glucose, and remember, glucose, if you've had biology, is the food of the cell, right? Then what happens is all the glucose goes inside the cell. And glucose solutions behave like pure water to the cell. So even though it may have the same concentration of solute, that is, has the same osmolarity, it doesn't have the same tonicity. It means the glucose essentially doesn't exist on the outside because it moves to the inside, carries water with it, and then gets consumed as a source of energy. So it behaves like distilled water. On the other hand, an ion on the outside that doesn't penetrate the cell wall, right? Its osmolarity, if it's isoosmotic, it's also isotonic in that case. But glucose goes inside the cell membrane. So you have to be a little bit careful. The book talks about these two things, hyperosmotic and hypertonic, and hypoosmotic and hypotonic, as being the same thing, but in medicine and in like health areas, these are not the same thing. They're slightly different. Anyways, just thought I would bring that up and show you what it looks like, right, when you're looking at actual cells, and these solutions are either hyper or hypotonic. So we're going to calculate the osmotic pressure of a solution that contains 18.75 milligrams of hemoglobin in 15 mils of solution at 25 degrees Celsius, and it says the molar mass of hemoglobin is 6.5 times 10 to the fourth grams per mole. So to begin with, we know osmotic pressure, right? Pi is equal to M times R times T, and T is 298.15 Kelvin. Now, to get the molarity, R is 0.08206 liters atmospheres over moles times Kelvin, like that. So I just need to calculate the molarity of the solution. So to get moles, right, I have 18, this will be my moles. I have 18.75 times 10 to the minus third grams. That's again, substituting the definition of a milligram, and then I know it's 6.5 times 10 to the fourth grams for every 1 mole. That gives me 2.88 times, let's see, 10 to the minus 7 moles. And then to get the molarity, I have 2.88 times 10 to the minus 7th moles divided by 15.0 times 10 to the minus 3rd liters. And that gives me 1.92 times 10 to the minus 5th. And that will be in moles per liter or molarity units. And now all that's left to do is plug it into this equation. So I have pi equal to, and I'll just write it all out, 1.92 times 10 to the minus 5th molarity times 0.082061 liters times atmospheres over moles times Kelvin times 298.15 Kelvin. That leaves 4.7 times 10 to the minus 4 atmospheres. Oftentimes this is calculated in millimeters of mercury or in torr, and that's actually I'll write it above here, 0.358 torr, like that. Either one of these, depending on the units that are in the back when you look it up. This is actually one of the even number problems out of your book. All right, so again, pretty straightforward. Strategy similar to what you might expect. You need to find the molarity, which means you need to find the moles. You're given grams or milligrams, so we convert milligrams into grams and into moles using the given molar mass. Then we divide by the volume to give us some molarity, and then plug it into the equation and finish your calculation.